I don't think so.
You say tomato, I say tomato. But I'll go on and say
But the point is that tomato, regardless of how it's said, it is a fruit and not a vegetable, apparently.
What is?
Tomatoes. But greetings and welcome, friends. Regardless of your stance on the tomato topic, we still welcome you all here to learn math. And today we're talking about graphs of polar equations. And we're doing essentially two examples, and I'm going to do a little bit of discovery manipulation in Geometer Sketchpad and make a table for us. It'll be great. But here we go. Let's graph the equation r equals sine theta. So we graphed some equations yesterday where if I had r equals a number that was a set radius and the graph was a circle at the center of the pole, so to speak. And if I had theta equal a number, then it ended up being a line of all the points that were at that angle like that. But now I've got like some modifications going on here. So let's see what occurs when I try to graph r equals sine theta. Now, a majority of this can be done using some sort of table of values approach. Oh, whoa, that's not what I meant to do. But I'm actually going to instead have us represent this somewhat graphically, rectangularly first. Oops, I'm pasting this in all the wrong places. Here we go. So let me graph a rectangular version of this for starters.
Wait, this is what we're not supposed to write down?
No. Let's write down a little table. It's just the classic 1 to -1 and out to 2 pi sort of situation. And what I'm going to do is let's graph y equals sine x. And then I'll pull that back into an r equals sine theta sort of relationship and graph it polarly, so to speak. So y equals sine x, you might remember the graph of sine starts at 0. It goes up to 1 at pi over 2, or 90 degrees. It goes back down to 0 at pi, or 180 degrees. And then it goes back down to -1, or I guess the first time it's at -1, so it didn't go back there. It's at -1 at 3 pi over 2, or 270 degrees, and then back to 0 at 2 pi. And you might know some of these other values. For instance, at pi over 3, sine of pi over 3, or sine of 60 degrees, it's root 3 over 2, which I think is like 0.70, oh no, sorry, 0.83, something like that, I think. At, let's see, this is pi over 2. Here's pi over 4. It's 0.707, I believe, root 2 over 2. And then it's a half at sine of 30 degrees, which would be pi over 6. So here it would equal a half. And we'd be able to draw the curve something like this. And that's an ugly sine wave, but it's good enough for me. So I just want to have a general idea of what these points are for this, because the height of this graph, or the y value of this graph, when I try to graph this polarly, is going to be the radius. So what's going to be happening is my radius is going to start at 0, then the radius is going to go to a half, then the radius is going to go to 1, then back to 0, then to -1, and back to 0. So the radius of this graph is variable. It's changing over time as a result, and it's changing in accordance to sine of the angle. So this is going to be quite intriguing, I think we'll agree. So let me get a nice little polar graph here. Feel free to use one of the ones from the sheet that I'd given you earlier. Although actually in this case, I only need to go out to 1 for all of my radial points, I suppose. And so take a look at this. So I'm graphing r equals sine theta. Right, and I could have made a table of values where I plug in a bunch of thetas, get a bunch of r's, and I just plot all the points like that. But I think it's a little bit interesting to see it done in this approach graphically. So when theta is 0, what was sine? Let's look here. 0. The height was 0 there, right? So that means at 0 degrees, I'm at 0. So 0, 0 for my r theta. That was easy so far. When theta is pi over 4, then the output was 1/2. So sine of pi over 4 is 1/2. So when I'm at a pi over 4 angle, which is at a 45-degree angle, I'm expecting to be out at 1/2. All right, so something happens between here and here. I doubt it's just a straight line. Well, because, yeah, it's fluctuating through those angles. But it's probably something like this, considering that the radius is increasing from there to there. That would make sense. So when theta is, let's say, pi over 2, it's at 1. So pi over 2, a pi over 2 angle is right here, 90 degrees. So at 90 degrees, I'm going out 1 unit. So this is interesting so far. Actually, let's throw in the 60-degree measurement there, why don't we? What is sine of 60 degrees, or sine of pi over 3? It's 0.8-ish. So at this angle, I would have been out at 0.8-ish. Okay, so this is an interesting thing. So it appears to be following this sort of a trajectory. And now I know 1 is the largest the radius is ever going to get for sine, and now it's going to pull back, right? So let's see what happens on the rectangular graph. At pi, it's going to be all the way back down to 0. So when I'm facing this way, I'm going to have a radius of 0. Let's try to get, yeah, bless you. Let's do 3 pi over 4, let's say. What's the value at 3 pi over 4? It's the root 2 over 2. Actually, guys, you know what? I plotted this point at the wrong spot. How embarrassing. There it is. And then yeah, it was around 0.8-ish, and then it's 1. Sorry, I didn't have 30 degrees. I had 45 degrees. So 45 degrees, it was at root 2 over 2, which is 0.7-ish. So here's 0.6, here's 0.7. So at 45 degrees, it was somewhere like that. And let's see, so at 135 degrees, it's also at 0.707. And then it comes down. So it turns out this graph is a circle that does not have its center at the pole. Isn't that kind of crazy? Like, this distance was my variable r over time, right? Like, r increased to 1 and then r decreased, and all in a matter of 180 degrees. All I've done was gone from 0 to pi, right? I've only done this angle, and I've gotten this circle. Okay, well, let's keep going. What about 5 pi over 4? I'm negative root 2 over 2. So 5 pi over 4 here is this 45-degree angle, right? So here's 5 pi over 4. Somewhere out this is the direction I'm looking, but the value is negative 0.707. Where's negative 0.707 according to this angle? It's back this way and lands exactly on the same point I already have. That's not the 45. You're right. But thank you for your honesty. There we go. There we are. Or if I was at 210 degrees, I would have had negative 0.5, and I would have mapped backwards to this spot. So it turns out, as I'm looking in these directions, it's getting mapped out to these points a second time, and it loops around the circle a second time, which is craziness. All right, so it turns out that because of the negative r values for this whole quadrant, it remaps the circle exactly back onto itself. So I just want to point out that's what's going on, and my circle came out a little bit sloppy. But if you wanted to see an actual exact graph, it's actually literally a perfect circle that comes out of this, which I think is unexpected. Yeah, it's got a little bow tie. Isn't that cute? Yeah, those are just like little arrows they drew. And what I want to point out is it did one full revolution from 0 to 180 and another full revolution from 180 to 360. So it actually mapped over this circle twice. So my domain, to get the full path, I only need to go from 0 to 180 to get the full set of outputs for the R, oddly enough. So that's my first concept that I wanted to show you. Let's look at another example. Yeah, cosine, I'm not going to end up doing, but R equals cosine theta will actually also be a circle, except it will be off on this side. It'll be this circle for cosine, something like that. So let's do, well, it'll have cosine in it, but it'll have some other friends hanging out with it. And perhaps some unexpected behaviors will result. Shenanigans will be had by all. So you guys might not remember all of your abilities of graphing cosine functions. So let's see, this is an upside down cosine function because of the -5. Let me just, I'll throw some of these in here. Let's first graph a rectangular version of this if this was a y and this was an x, okay? So I'm going to go from 0 to 2 pi. Notice my kind of values are all shifted around here. So what I'd want to point out, and actually I don't remember what we called all of these variables, but if this is y equals, maybe I'll write it this way, I'll even write it in blue, why not? Y equals -5 times the cosine of x plus 3 on the outside of that. What I've got going on here is the amplitude is 5. It's flipped upside down. And it's been shifted up 3. Okay, so that's kind of what's going on there. You might remember how there was ways to do phase shifts and stretch and smoosh in different directions, but I'm not worried about that. So because the shift up 3, it turns out that the midline, wow, I almost forgot what that was called, occurs right there. So at 0, cosine starts at 0, cosine starts at its maximum value, which is the full amplitude, except in this, so a regular cosine function would have looked like this, something like this, all right? Or, you know what I'm saying, right? This is a regular cosine, but it's also upside down, so I actually have to start at the lowest point. The amplitude is 5, so 5 less than the midline is actually at -2. And then at pi over 4, it's going to go to 0. At pi, it's going to be at its maximum point, which is 5 more than the midline, which is 8. And then at 3 pi over 4, it's at 0 again. And at 2 pi, it's going to be 5 this way in this case, because of the upside down nature. And so the general cosine curve is going to look something like this. I don't like that last part. Yeah, I could see that. All right, so that's what's going on. And now what I want to point out about my bringing it back to this, my R values, so my radius is negative, becomes 0 at some point, and then it's positive, but it actually gets more positive than it ever was negative for this, right? So my R values are actually shifting around again. So the R's are going to change depending on the angle when I pull this into polar kind of perspective. So here we go. Now, what's the maximum radius I'm going to have for this graph? What was the maximum y value on this rectangular version? 8. So for my polar graph, I'm going to have to go out as far as 8 is what I'll need to do. So let's see if we can figure this out. So at 0 degrees, I'm down at -2. So 0 degrees, I'm facing this way, but I'm going backwards too. So I'd plot a point right here. Does that make sense? Okay. So there's my first point. At, let's say this looks like pi over 4. So here's pi over 4. I'm facing this way. My value is still going to be, it's like around negative 1-ish. I'm just going to roughly ballpark this. So negative 1-ish for that. It crosses 0 somewhere there. So it's actually, that means it's going to be, at some point, r is equal to 0. Do you guys agree? So it looks like this is doing like this shape, because r is 0 somewhere in this angle. And then r is, let's see, here's pi over 2, so 90 degrees. And it looks like the r value is around 3. Yeah, it is. And so pi over 2 is 90 degrees. That's this angle. So I'm facing up, and I'm going out a positive 3 units. Now there's angles between here that if I hit, it was positive. So actually this part of the graph would look like this. So it looks like I've got some weird thing going on here so far. Okay. Now let's see, at pi it goes out as far as 1. And that's the maximum distance, or sorry, 8, my apologies. So pi is the angles all the way out here. When I'm looking in this direction, I'm going to go out 8 units, 5, 6, 7, 8. So between here and here, the radius is still increasing more and more until it reaches 8. Okay? So this is really weird graph so far. I think you'd agree. And then it's going to start decreasing until I get to, what's this? Oh, 3 pi over 2. It's going to be back down to a 3 value. So let's see, 3 pi over 2, where's 3 pi over 2? 3 pi over 2 is all the way facing this direction, down. And it's going to be a positive 3, and I'm facing in that direction, so it is actually here. It's not negative and mapped back onto itself. And then so it looks like it's getting smaller for all of these angles until it hit there, right? And then it hits 0 at some point, and it's going to get smaller and smaller for these angles until it hits 0. And then it goes negative as I'm looking out in these directions, right? And it's negative, and it'll actually map back to the negative 2. So I get like this weird, I don't know if it's a shell or like a loop with a loop in it, whatever you'd want to call that, but that's what I end up getting. And it's a smooth curve, and this one takes the full 360 degrees before I was actually able to get the whole mapped path. Whereas the circle from earlier, it actually mapped over itself twice between 0 and 360 degrees. So let me show you a computer-generated image of this one. Like so. There we are. So it's a nice smooth curve that we end up having. You could do these with tables of values if you don't like doing it kind of rectangularly this way. I find that this is kind of interesting representing it that way, but the book literally directly just makes a table of values, and then you're just plotting a bunch of r's and thetas until you draw your curve. So yeah, so it started here, it went this way. And later on, we'll actually, I believe, do parametric polar. So we'd actually follow the path of an object moving this way as time changes. Craziness, I know. So, so that's good stuff. Let me show you. I've actually got this cool little geometer sketchpad thing going here. Let me actually scroll over here. And we're going to tinker around with some values. Let's see. There's geometer sketchpad. So I'm doing the sine versions. And I've got a couple inputs here, A, B, and N. And for sine, I currently have the value of A is set to 0. So it's more similar to what we had before. The value of B is 2 and N is equal to 1. So let's see, what appears to happen as N changes? Or sorry, the B, my bad. My B, as some might say. Yeah, it appears as though the maximum radius is directly related to B in this case, because, right, sine fluctuates between 1 and negative 1, so 1 times whatever B is going to give me my maximum R value at any point. And actually, oddly enough, what do you think is going to happen when B goes negative?
Only 1 point in the graph.
Yeah, it actually just makes a circle in the other direction. So that's what B seems to be doing. It's just scaling it, so to speak. So let's have B equal to 1. Let's change what A is. Okay, so there's A equals 1. This is actually called a cardioid. Kind of looks like a butt. But if it was upside down, it would be like a heart. Aw, how adorable. Actually, I wonder if I can accomplish. Oh, there we go. So it's called a cardioid, literally from like cardiac arrest, heart shape. Think that sort of concept. And whoa, I've got all sorts of interesting stuff going on here. Just let's tinker around with this A value first. So it looks like A does some different stuff. It shifts around, and it's just kind of like your flat scale of increasing the R by a factor all the time. And there's actually going to be relationships when A and B are equal, when A and B, one's bigger than the other. So yeah, let's check out, let's actually make A 2. And when they're equal, that's when I get like the cusp, where it comes to a sharp point and then cuts out. When it was a little bit different, this is actually a smooth transition here. So it's not a cusp, so to speak. And then past that, notice the cusp actually becomes an inner loop the moment B becomes larger than that, oddly enough. So that's some interesting stuff that goes on. So as those shift, you can get like this inner loop when the value of B is beyond the value of A. And that has to do with like kind of negative R values and looping around backwards and stuff like that. So that's kind of some unusual behavior. Let's see what this N value does. What?
Butterfly.
Yeah. So this is like a flower, and these are actually literally called petals for these types of graphs. And think about what N does. N is forcing me to cycle through the period of the sine function twice as fast. So it's going through its whoop, whoop, like twice as quickly, and that means the circle's no longer mapping onto itself. It's mapping in different quadrants now, effectively. And actually, it's hitting different quadrants at different times. It's actually not drawing the petals this way. I think it's hitting, positive, what would it be for sine? Yeah, it'd be positive, positive, and then here it would be negative. Yeah, wait a minute. Man, my mind's blown right now. I can't quite think about it. We're actually going to do some work with that a little bit later, mapping those points. But notice what happens with N as I change it. 3, I get 3 petals. 2, I got 4 petals. 1, I had 1 petal, if you want to think about it that way. So 2 is 4, 3 is 3, 4 is 8, 5 is 5 petals. What do you think is going on? It seems like when I have an odd N, what's the number of petals?
The same as an odd number.
Right, so 1 was 1 petal, 3 was 3 petals, 5 was 5 petals, 7 is 7 petals. And then the evens, the number of petals is just what? Twice the value of N. So I actually have a 12 petal figure going on here. So all sorts of weird stuff, and then I can actually mix the petals with different, so I can scale it. But if I add, watch this, you can actually get crazy inner petals and all sorts.
Artwork.
Yeah. Yeah, here's like what an evil Squidward you saw there.
First time Matt existed.
Evil. Okay, yeah. Here's Squidward's nose and his 2 eyes. I like it. Yeah. We'll officially call this the evil Squidward graph. I like the idea of that. So, Mammoth, unrelated to Squidwards, but who knows why? I don't know. Did they ever find mammoths in Bikini Bottom? Like, is there any archaeological discoveries in Bikini Bottom? Who knows? But yeah, there's a variety of different graphs that you can get. Good stuff, and all functioning from this. This is the smoothest transition going on. People at home have no idea what happened. So let me show you this. Let's see. Oh, can I access this? Nice. Actually, I might be able to get a better snapshot from this. So I've got, let's see, my computer's pinwheeling. So if you wanted one of each of those, you could have it. So there's a variety of different types of graphs that occur. They actually have different names, which is crazy. And fortunately, I'm not going to require that you memorize all of these names, and you're welcome. You're welcome. Yes, actually, yeah. Let's give credit due to where credit's due, sort of thing.
These are not functions because
These, actually, that brings up a really interesting question. Rectangularly speaking, these are definitely not functions. So yeah, so this is a lemniscate. I don't remember. Lemniscate. It's like a biscuit, apparently. I don't know. Maybe not at all. Infinite lemons. Every villain loves. Every villain is lemons. Maybe. This is called a limousin. That's like a soft C. Actually, technically, the symbol on that C is like one of these crazy ones with like a weird little. Yeah, my foreign friends. What does that letter is called? Does anyone know that letter? Sure, I trust you.
yeah, I don't know in English.
Oh, you don't know it in English? Well, anyways, it's basically like a magnifying glass symbol, except it's a broken magnifying glass. So yeah, this is a limousin, and that's when it's got the inner loop. And there's types of limoussins that are a subset of the limoussins, should I say, are the cardioids. And the cardioids, as we saw, were the heart-shaped ones. Good stuff. So here's the cardioid. Here's the graph that's shown is a cosine cardioid because it's opening to the right, or so to speak. And then another interesting graph, unrelated to the trig functions, is the spiral of Archimedes, which I think is really cool. And this function can be used to model like mollusk shells and different things like that, or snail shells, or different creatures, or the spiral arms of the Milky Way galaxy, different things like that. Which actually, oddly enough, little side fact about spiral galaxies is no matter how far they are from us, okay, whatever number of light years into the past we're looking, they still have spiral arms, whereas spiral arms actually should have dissipated within a certain number of millions of years. So the fact that the ancient galaxies still have spiral arms is really weird for us to think about, and it really it kind of messes with the age of the universe in calculations like that. But anyways, yeah, right there. So r equals a times theta. Imagine this: the bigger the angle gets, the bigger the radius is. I'm just like, the radius is getting larger and larger and larger as the angles increase, and actually, this literally would keep spiraling around itself at a bigger and bigger spiral as time goes on. So that's some of the names of these general shapes. You don't have to know them. It would be cool perhaps if you could recognize them maybe by function using this table tonight when you're doing your homework, that you'd know what kind you're getting. But whether you graph tonight using a table of values, or like you saw me doing, where I was kind of graphing the rectangular version first and then using the y coordinate as my r, whichever approach you take would be fine, and I'm cool with that. So, anyways, thanks for watching, Internet friends. We hope you have a very great day. Bye-bye.